Let's keep rolling with this example. So we have another quadratic inequality. So first thing we would want to do is forget about the inequality for just a second so that we can find the points where it crosses the axis. So I'm going to set this equal to 0. All right, so I'm looking for two numbers that multiply to 16 and add to -8. So 4 and 4, and if they're both negative, so we have x minus 4, x minus 4. Now remember, if we have two of the same factor, we can just write that as x minus 4 squared. And then when we're solving the equation here, we can take the square root. Because it's 0, we don't really have to worry about the plus and minus. And we very quickly get that x equals 4. So even though this is a quadratic, remember that they don't always have to have two real roots, or they can have one real root with a multiplicity of 2. So we only have one point here that's going to break up our interval. So that should actually make our life a little bit easier. So again, I'm going to put 0. Here's x equal 4. This is my boundary. Again, on the left side, this would be -infinity, and we go up to 4. And then it is an inequality with an equal to, so I'm going to include 4. And on the other side, I'm going to include 4, and I go to positive infinity. And that's a parenthesis, by the way, just to be clear. Okay. So I do the same thing, but this time just with two intervals. So let's start off with that interval. We have -infinity to 4 and 4 to infinity. We need a test point. I'm going to choose 0 in this interval, and I'm going to choose 5 on this interval. Then we have the actual equation that we're going to plug into. And let's do this in factored form. It's always easy to substitute into that one a little better. All right, that's the same equation as x squared minus 8x plus 16. All right. And then last part is, do we include, right? All right. So let's take 0, substitute it into the equation. So 0 minus 4 squared. That's going to be -4. -4 squared is 16. That is true. And therefore, we include this section. What about the 5 if we plug that in? So we do 5 minus 4 squared. That's going to be 1 squared, or 1. That's also true. So we include this section. So where would this really be important? Well, because this inequality is greater than or equal to, and both of these seem to be included, then we can just say the solution set is -infinity to infinity. If instead the problem was not equal to, right, if it was just greater than, then our solution set, right, so we'll say if the original problem was just this, the solution set would be a little different. It would be -infinity to 4 and 4 to infinity, not including 4. Okay. Let's go ahead and take a look at the graph to match up with what we found. This is our curve. You'll see it's all above the axis, except where it touches the axis. So that's why if it says greater than or equal to 0, we can include that point. If it's just greater than, we cannot include this point. It would be everything on the left and everything on the right. I think we have one more example here. Again, well, first off, right, we're going to say equals 0, right, for the purpose of solving. Then everything here has an x in common. I'm going to factor that out. And now it looks like I have to do grouping here. So I'm multiplying these two. So I need something that multiplies to 12 and adds to 8. Can I think of two numbers that do that? Well, how about 2 and 6? So I will replace the middle term with a combination of those two. And it doesn't matter which order you put them in here. It doesn't matter if I do 2x and 6x or 6x and 2x, it'll work out just fine. Okay. So now I'm just going to include a bracket here just because I want to distinguish, right? I want to group the first two and group the second two. All right. The first two have what in common? Well, it looks like they just have an x in common. That leaves me with 3x plus 2. What about the second set? Looks like I can take out a 2. That'll leave me with 3x plus 2 again. And that's perfect. That's what I needed it to do. So I have x times, one of the factors is 3x plus 2. The other factor is x plus 2. And once I've done that, I don't need this bracket anymore. I have now factored this completely. And I can solve for my values, my boundaries. So x equals 0. Hopefully that's obvious that that's one of them. Then 3x plus 2 equals 0. Solve for x. And we get negative 2/3. And then x plus 2, solve for 0. I'm sorry, solve for x. And we get this. So what would our number line look like? Okay, well, let's do our number line here. Let's find 0. Negative 2. And let's say 1, 2. So this is a boundary. This is a boundary. And then negative 2/3. So here at negative 2/3 is also a boundary. So this time we have 3 boundaries, which means we have 4 intervals. Let's name them. And let's just go ahead and maybe jump down to our chart here, and I'll start building that. So interval, test point. The function was x times 3x plus 2 times x plus 2. And the inequality was less than 0. Okay. So we want to know, when is this true for what test points, and then whether we include those points. So what I'm going to do is I'm going to come up here, I'm going to grab my number line and move it down so we can see it while we are trying to determine our intervals. Okay. So the first interval looks like it's going to go from minus infinity up to negative 2. And again, because it's not equal to for the inequality, right, I'm not going to include any of these values. The next interval is -2 to -2/3. Then from -2/3 to 0. And finally, from 0 to infinity. All right. At this point, if you'd like, maybe pause, pick some test points, try this out yourself. I'm going to choose -3 for this region, right? That would be right here. Between -2 and -2/3 is -1. That's probably the easiest value to use there. Between -2/3 and 0, I think maybe -1/3 would be a good choice. And from 0 to infinity, 1 is hopefully the obvious option there, right? But clearly you have infinite numbers that you can choose. All right, so let's plug these in and see what we get. So this would be -3 times 3 times a -3 plus 2 times -3 plus 2. Oops. Just less than there. Okay. -3 times 3 is -9. -9 plus 2 is -7. So we have -3 times -7 times -1. 3 negatives multiplied together are going to remain negative. So 3 times 7 is 21, and then times a -1. So we have -27, which, and I keep doing that, which is indeed less than 0. So if that's true, we include. All right, let's plug in -1. So -1 times 3 times -1 plus 2, -1 plus 2. 3 times -1 is -3, plus 2 is -1, and -1 plus 2 is 1. We end up with 1 is less than 0. That is not true. We do not include that region. All right, -1/3. 3 times -1/3. And -1/3 plus 2. So we end up with -1/3. 3 times a -1/3 is just -1. Plus 2 is +1. And then -1/3 plus 2. Well, 2 is 6/3 minus 1/3 makes +5/3. So this all results in -5/9, which indeed is less than 0. So we include that region. Finally, we need to plug 1 in and see what happens. So let's do that as well. So we have 1 times 5 times 3. That's going to be 15, which is not less than 0. We do not include that section. So our solution set includes the first interval and the third interval. So if we were to write that, right, the solution set is -infinity to -2, union -2/3 to 0. So we're talking about this region and this region. Let's look at the graph. So again, I've already plotted. This is our function. You'll notice from -infinity up to -2, and this is indeed less than 0. It's greater than 0 between that and here. It's less than 0 between these two values, which is -2/3 and 0. That's what we just stated. And then again, it's positive above. So the solution set is this region down here and this region here below the axis.